Right now, beneath the soil of some of the most heavily farmed land on Earth, there is this toxic legacy from the 1960s that's just quietly seeping into the drinking water.
Yeah, and it's completely invisible. It has no smell, it has no color.
Exactly. But once it gets inside the human body, it literally hijacks your blood's ability to carry oxygen. I mean, today we are looking at an invisible crisis, and we are so glad you are joining us for this deep dive.
It really is the kind of threat that just completely shatters our basic assumptions about safety. Most of us rely on a really simple visual test when we turn on the tap. If the water is clear, we assume it's clean.
Right. Which makes sense.
Right, but when you step into the world of hydrogeology and environmental toxicology, you quickly realize that clarity is, well, it's often a very comforting illusion.
Yeah, and we know you're here because you want those real aha moments, the deep understanding of a complex issue without having to sift through a mountain of academic jargon. So we have a really fascinating mission for you today.
We absolutely do.
We are unpacking this massive, first of its kind, 2025 systematic review. It was published in the journal Water, Air, Soil Pollute. And this team of researchers, they synthesized 90 recent studies on water contamination across 16 different Indian states.
And their primary target in all of this is a chemical called nitrate.
Right. And we aren't just going to look at where this is happening. We're going to explore the actual mechanics of how it infiltrates the ground, what it physically does inside your body, and the real-world solutions scientists are proposing to actually fix it.
So to fully grasp the stakes of this review, we should probably set a quick baseline for what nitrate actually is.
Okay, let's do it.
At its core, it is a naturally occurring compound, just made of nitrogen and oxygen. And, in a perfectly balanced ecosystem, it is a fundamental nutrient. Plants absolutely need it to grow.
So it's not inherently evil.
No, not at all. The problem we are facing isn't some freak occurrence of nature. It is a problem of our own making.
Yeah.
I mean, human activities over the last several decades have radically altered the global nitrogen cycle. We've taken this vital natural nutrient and basically turned it into an aggressive, pervasive environmental pollutant.
And to understand how that transformation happened and why this has become a full-blown crisis in India, we kind of need to picture the ground beneath our feet differently.
How so?
Well, think of the earth not as a solid barrier, but as a giant, slow-drip coffee filter. When we spray chemicals on the surface or, dump waste on the dirt, those substances don't just sit there.
Right, the water moves them.
Exactly. Every time it rains or every time a field is heavily irrigated, that water acts like the hot water in your coffee maker. It just pulls everything on the surface down through the soil, layer by layer, directly into the underground aquifers that feed municipal water supplies and rural wells.
That analogy perfectly captures the mechanism of leaching. And the materials filling up that metaphorical coffee filter are almost entirely anthropogenic, meaning human-made.
Like what? What's driving this?
The researchers highlight a few primary culprits, but the absolute biggest is intensive agriculture. If we look back to the grain revolution in the 1960s, there was this massive, necessary surge in the application of synthetic nitrogen fertilizers.
Right, to boost crop yields and feed a rapidly growing population.
Exactly. But plants can only absorb so much nitrogen. The excess just simply sits in the soil. So over decades, that unused fertilizer has been migrating downward.
Through the coffee filter.
Yep. And then you combine that agricultural runoff with rapidly urbanizing areas that suffer from inappropriate sewage disposal, untreated industrial waste, leaking septic tanks, and you have a recipe for widespread contamination.
I was actually looking at the geographic data the researchers mapped out across those 16 states, and the disparities are jarring.
They really are.
For example, in Rajasthan, the mean nitrate concentration in their water was almost 80 milligrams per liter. And some individual samples were spiking up to over 180.
Which is astronomical.
Yeah. And then you look at Uttar Pradesh, specifically the Gautam Nagar district, and they recorded a peak value of nearly 200 milligrams per liter. But then you glance over at a state like Uttarakhand, where the mean is barely over 2, or West Bengal at around 8.
Well, and those numbers become incredibly alarming when you place them next to international safety standards.
Oh, right, because there's a limit to what's safe.
Exactly. The World Health Organization sets the safe limit for nitrate in drinking water at just 10 milligrams per liter.
Wow. Only 10.
Yeah. Now, the Bureau of Indian Standards is more lenient. They allow up to 45 milligrams per liter.
That is a massive gap in safety thresholds. 10 versus 45.
It is, but the real tragedy here is that even with that much more lenient 45 milligram standard, 13 out of the 15 states with complete data in this review completely failed to meet it.
That's devastating.
So when a community in Uttar Pradesh is pulling up water with nearly 200 milligrams of nitrate per liter, they are pulling up something fundamentally toxic.
I'm looking at this data, and honestly, the geographical differences make no sense to me. Like, Rajasthan is spiking dangerously high, but Uttarakhand is basically safe. What is Rajasthan doing so differently? I mean, they're both agricultural regions, aren't they?
They are, but agriculture is only one piece of the puzzle here. It really comes down to how farming practices intersect with local geography and infrastructure.
Okay, break that down for me.
So Rajasthan is a largely semi-arid region, right? When farmers there apply heavy synthetic fertilizers and then rely on intense seasonal irrigation or sudden monsoon rains, you get highly concentrated leaching.
Because it's all washing down at once.
Exactly. And furthermore, their deeper aquifers don't always have a rapid recharge rate with fresh, clean rainwater to dilute those chemicals. So the water just sits there, getting more toxic over time.
Wow. And what about Uttar Pradesh? Because their numbers were insane.
Uttar Pradesh illustrates a different pathway entirely. The study explicitly linked that massive, near 200 milligram spike, not just to farming, but to poor sanitation infrastructure.
Oh, wow.
Yeah, they are seeing the direct result of human and animal waste leaking from the surface directly into the groundwater. It is this perfect storm of heavy farming above and a failing sanitation below.
Okay, so we have these terrifyingly high numbers in places like Rajasthan and Uttar Pradesh, but, standing over a rural well with a test tube is very different than predicting if the person actually drinking from it will get sick.
Right, the environmental data versus human impact.
Yeah. So how do scientists bridge that gap? Like, how do they quantify the actual danger to you, the individual who's turning on the tap?
Well, they bridge that gap using a highly standardized framework, which is called a human health risk assessment. The researchers utilized a model developed by the U.S. Environmental Protection Agency.
Okay.
And while the math behind it is incredibly dense, it essentially boils down to two vital metrics. The first one is called the chronic daily intake, or CDI.
CDI. Got it.
This calculates the actual dosage. It measures how much of the contaminant you are ingesting every single day, and then it adjusts that for your specific body weight.
Oh, that makes sense. Because a grown adult drinking a liter of water is obviously experiencing a completely different dosage than a toddler drinking that same liter.
Exactly the point. The second metric is the hazard quotient, or HQ. And the HQ takes that dosage, your CDI, and compares it against a rigorously established safety threshold.
So it's like a ratio.
Yes, it is a ratio. If your total hazard quotient is less than 1, the math suggests you are in the safe zone. But if it creeps above 1, you are officially at risk for adverse, non-carcinogenic health effects.
And the researchers didn't just assume people were only drinking this water, right? I mean, they evaluated 2 different exposure pathways, correct?
They did. They looked at the dermal pathway, which measures exposure through the skin when people are, bathing, showering, or washing clothes. And then they looked at the oral pathway, which is ingestion through drinking and cooking.
This was honestly one of the most surprising parts of the review for me. You hear about water with 200 milligrams of nitrate, and the idea of even taking a shower in it sounds horrifying.
It does sound bad, yeah.
But the study found that dermal exposure poses almost 0 risk. Across the board, in every single state, the dermal hazard quotient was well below 1. The danger is almost entirely from drinking it.
Yeah, the human skin is an absolute marvel of biology. It acts as an incredibly effective, near-impermeable barrier against certain water-soluble compounds like nitrate.
That's fascinating.
The absorption rate through the skin is negligible, and this actually gives public health officials a very clear, actionable mandate. I mean, you don't necessarily need to condemn an entire municipal water supply for all uses immediately.
Right, you don't have to ban showering.
Exactly. The absolute uncompromised priority has to be securing safe drinking and cooking water.
Okay. Let's unpack this demographic data, because this is where I actually found myself totally confused and had to basically reread the section.
Oh, really? What part?
So they broke down the total hazard quotient by age group. You've got infants under 6 months, children from 7 months to 17 years, and adults. I automatically assumed that infants would be the most vulnerable group.
Most people do.
Right. But the data shows that children, that middle group, are facing the highest non-carcinogenic risk. Why on earth are teenagers and school-aged kids showing higher risk levels than babies?
It seems totally counterintuitive until you look closely at the math behind that chronic daily intake we talked about. Remember, CDI is ingestion rate divided by body weight.
Right.
Well, children and teenagers are incredibly active, their metabolisms are running high, and they drink a massive amount of water every day. However, they still have a relatively low average body mass compared to a fully grown adult.
Oh. So they are taking in adult volumes of water, but putting it into a fraction of the body mass. It's an exposure multiplier.
Yes, it mathematically forces their dosage through the roof. An adult might drink the same amount, but their larger body mass dilutes the systemic impact.
And what about the infants then?
Well, an infant has very low body mass, obviously, but their direct tap water intake is usually much lower because they rely heavily on breast milk.
Ah, that makes sense.
Now, if an infant is drinking formula mixed with contaminated well water, that is a uniquely dangerous scenario we will cover in a moment.
Yeah.
But strictly looking at the daily tap water ingestion, the school-aged children are taking the biggest hit. Their hazard quotients were the highest across the board.
Man, okay, so we know they are drinking it, and we know their dosage is alarmingly high. What actually happens inside the body once that water is swallowed? Because the health consequences detailed in this review go way beyond just an upset stomach.
Yeah, the review outlines a devastating cascade of biochemical reactions. The fascinating and honestly terrifying thing about nitrate NO3 is that it is relatively inert on its own.
Really?
Yeah, if it just passed through you, it wouldn't be a crisis. The cascade begins the moment it interacts with the bacteria naturally living in your saliva and your digestive tract.
Oh, so our own bodies trigger it.
Exactly. Those bacteria chemically reduce the nitrate, stripping away an oxygen atom and basically converting it into nitrite, NO2.
And nitrate is the actual threat here.
It is the catalyst for the entire health crisis. Once that nitrite enters your bloodstream, it aggressively targets your hemoglobin. And, hemoglobin is the protein complex inside your red blood cells that is responsible for carrying oxygen from your lungs to the rest of your body.
Wait, hold on. Let me make sure I understand this process because the chemistry gets dense. If my red blood cells are essentially a fleet of delivery trucks meant to carry oxygen to my organs,
Yes, great analogy.
is the nitrate sneaking into the depot and somehow changing the locks on the trucks?
That is a brilliant way to visualize
Yeah.
it, yes. The nitrate chemically oxidizes the iron inside the hemoglobin. It fundamentally alters the lock, transforming normal hemoglobin into something called methemoglobin.
Methemoglobin.
Right, so your red blood cells continue to circulate through your bloodstream, but those delivery trucks are permanently locked. They cannot pick up oxygen from the lungs, and they cannot deliver it to the tissues.
They're literally just driving around empty while the body suffocates.
Precisely. And when a significant percentage of your blood is converted into methemoglobin, you develop a severe condition called methemoglobinemia.
Which is commonly known as blue baby syndrome.
Exactly.
Which brings me back to the infants. If children have the highest dosage, mathematically, like we just discussed, why is this specific syndrome so famously lethal to babies under 6 months old?
Because it shifts from a mathematical risk to a strict physiological vulnerability. An adult or an older child has a specific, naturally occurring enzyme in their blood that essentially acts as a master key.
Oh, interesting.
Yeah, it can constantly convert that hijacked methemoglobin back into normal hemoglobin. It unlocks the trucks.
But the babies don't have it.
Right. Infants under 6 months old have severely underdeveloped enzyme systems. They physically lack that master key. So if nitrite gets into their blood, say from baby formula mixed with contaminated water, the methemoglobin just builds and builds.
Because they can't reverse it?
Exactly. Their tissues are starved of oxygen, their skin takes on a literal blue tint, and without rapid medical intervention, the suffocation is fatal.
Wow. It is a totally preventable tragedy. But blue baby syndrome is an acute, immediate reaction, right? The systematic review spends a massive amount of time detailing the long-term chronic risks of drinking this water over years or decades. And this is where the discussion turns to cancer.
Right. While the hazard quotient measures immediate non-carcinogenic toxicity, the researchers are deeply concerned about the carcinogenic pathways.
How does that happen?
Well, when nitrite enters the highly acidic environment of the human stomach, it doesn't just sit there. It reacts with natural amines and amides from the food you eat to form highly potent chemical compounds.
What kind of compounds?
They're called N-nitroso compounds.
And I'm guessing those aren't something you want synthesizing in your gut.
Far from it. N-nitroso compounds are extensively documented potent carcinogens. They trigger severe chronic inflammation and provoke uncontrolled cell proliferation.
So they literally cause cancer.
Yes. The review highlights how chronic exposure to these compounds in drinking water is strongly linked to significant increases in the rates of gastric and colorectal cancers in these heavily contaminated agricultural regions.
And the damage doesn't even stop at the digestive tract, does it? I mean, the study maps out how this chemical basically goes on a tour of destruction through the endocrine and cardiovascular systems, too.
It acts as a systemic disruptor. Look at the thyroid gland, for instance. Your thyroid requires a steady uptake of iodide from your blood to produce the hormones that regulate your entire metabolism.
Right.
Well, nitrite molecules actually mimic the shape of iodide closely enough that they actively compete for access to the thyroid. They physically block the iodide from getting in.
Oh, wow. They just jam the receptor.
Exactly. Over time, this chemical blockade leads to severe hypothyroidism and the visible swelling of the neck, which is known as a goiter. And for pregnant women, this disruption to the metabolic hormones is linked to devastating reproductive outcomes, including preterm births and dangerously low birth weights.
And then it attacks the heart.
Yes, through the cardiovascular system. Your body relies on a natural nitric oxide pathway to keep your blood vessels relaxed and dilated. The nitrite from contaminated water disrupts this delicate signaling pathway, which results in severe vasoconstriction.
Meaning the vessels tighten up.
Yes, your blood vessels are physically forced to tighten and narrow, so the heart has to pump exponentially harder to push blood through those narrowed pipes, leading to chronic hypertension, cardiovascular hypertrophy, where the heart muscle unhealthily thickens, and a dramatically increased risk of heart attacks.
So we are looking at a chemical that suffocates cells, alters our blood, causes gastrointestinal cancer, and basically breaks our cardiovascular system. You obviously can't just tell millions of people living in these 16 states to just stop drinking water. How are scientists proposing we actually stop this?
Well, before we can even deploy a solution, we have to understand that nitrate rarely acts entirely alone. The review highlights a co-occurrence factor that complicates everything. It is the ultimate threat multiplier.
Meaning the nitrate is inviting other things into the water.
Yeah, it alters the environment to make it more hostile. When you continuously overload agricultural soil with synthetic nitrates, you fundamentally change the soil chemistry. You drastically lower the pH, making the ground more acidic, and you alter the redox conditions.
Wait, why does acidic soil matter for drinking water?
Because soil naturally contains trace amounts of highly toxic heavy metals, like cadmium and lead.
Okay.
Normally, those heavy metals are locked away safely. They are bound tightly to the dirt particles. But when the nitrate lowers the pH, it breaks those chemical bonds.
Oh, so the nitrate is essentially acting like a solvent. It dissolves the chemical glue holding those heavy metals in the dirt and allows them to be flushed right down into the aquifer alongside the fertilizer.
That is the nightmare scenario. You are no longer just trying to filter out nitrate, you are dealing with a mobilized toxic cocktail of heavy metals. This makes the engineering challenge of cleaning the water infinitely more complex.
Right. But here's where it gets really interesting to me. The researchers who authored this review, they don't just wave a magic wand and say every village needs a billion-dollar state-of-the-art filtration plant.
No, they don't.
They live in the real world. They recognize that you cannot slap a Silicon Valley tech fix onto a resource-strapped rural farming community in India. Their solutions are incredibly pragmatic.
They advocate for a tiered mitigation framework that's based entirely on local risk and available resources. India is incredibly diverse geographically and economically. A one-size-fits-all policy is guaranteed to fail.
Okay, let's look at their first tier.
Yeah.
The high-risk, high-capacity states. Places like Maharashtra or Telangana that have significant budgets and robust infrastructure. What are they proposing there?
For those regions, the researchers suggest leaning into advanced centralized interventions. We're talking about using artificial intelligence and machine learning algorithms to actually predict contamination events before they even happen.
Wait, how does AI actually predict water contamination? It's underground.
The AI models ingest massive, disparate data sets. They look at hyperlocal rainfall forecasts, track regional fertilizer sales data, analyze the specific porosity of the soil, and monitor real-time sensor data from the municipal grid.
That's wild.
Yeah, the algorithm can synthesize all that and alert a water treatment plant that a massive nitrate spike is going to hit a specific, well, say 3 days from now. And those high-capacity states can also afford to install and maintain centralized reverse osmosis and electrodialysis plants.
Which physically clean the water.
Exactly. They use advanced membranes and electrical currents to physically strip the nitrate and heavy metals out of the water at scale.
That is incredible technology, but obviously it requires constant electricity, expensive replacement parts, and highly trained engineers. What about the second tier? The high-risk, resource-constrained states. I mean, a place like Rajasthan has the highest contamination levels, but a rural village there doesn't have the budget for an AI-driven reverse osmosis plant.
Right. For those communities, the solutions have to be highly scalable, incredibly low cost, and easily maintained by the people actually living there. The review heavily emphasizes localized filtration, specifically using biochar and sand filters.
What exactly is biochar, and why is it useful in a rural village?
Biochar is essentially charcoal, but made from agricultural waste like leftover crop stalks or husks. The community can heat this waste in a low-oxygen environment. This creates a highly porous, carbon-rich material.
And they use that to filter the water.
Yes, when you pack that into a simple filtration column with sand, the biochar acts like an intense chemical sponge. As the water passes through, the microscopic pores in the biochar physically trap the nitrate and those heavy metals we talked about. It is cheap, it uses local waste, and it doesn't require a power grid.
That's brilliant. The review also mentions phytoremediation, which honestly sounds like science fiction, but it's actually just using nature to fight nature.
It is a phenomenal strategy. Phytoremediation involves strategically planting specific types of deep-rooted vegetation, like certain grasses or fast-growing trees, right around the agricultural runoff zones.
And they absorb the chemicals.
Yeah. These specific plants are hyperaccumulators. They act as biological vacuums, naturally sucking massive amounts of excess nitrogen out of the soil and surface water to fuel their own growth before that chemical ever has a chance to leach down into the deeper drinking aquifers.
Wow.
And if you combine that with aggressive rainwater harvesting to naturally dilute the existing groundwater and distributing cheap, color-changing nitrate test strips to households, you really empower a village to protect itself.
So what does this all mean for you listening to this right now? Why should you care about a systematic review of groundwater aquifers in India?
Well, if you connect this to the bigger picture, this highly localized issue of water quality is a perfect microcosm of our global struggle to survive our own progress. This review directly intersects with the United Nations Sustainable Development Goals, specifically SDG 6, which demands clean water and sanitation for all, and SDG 3, which focuses on global health and well-being.
Because everything is connected.
Exactly. The authors make a compelling case that you cannot achieve human health goals without first achieving environmental goals. You need hydrogeologists analyzing the water, talking to toxicologists who understand the blood, who are communicating with agricultural experts managing the soil, who are finally informing the government policymakers. It absolutely must be interdisciplinary.
The coffee filter is inextricably connected to the delivery trucks in your bloodstream. I love that. Before we wrap up this deep dive, I want to leave you with one final thought to explore on your own. Something the researchers only briefly touch on at the very end of their text, but which casts a massive shadow over everything we've just discussed.
Yes. The looming, unpredictable variable of global climate change.
Imagine the fragile, overloaded system we just mapped out. We have decades of legacy nitrogen fertilizer just sitting in the soil across these massive agricultural belts. It is a ticking time bomb. What happens when shifting global weather patterns bring sudden, unprecedented, violent, heavy rains and floods to these regions?
Well, the slow-drip coffee filter turns into a high-pressure espresso machine.
Exactly. How much more of this toxic legacy will be aggressively, rapidly flushed out of the dirt and straight into the drinking water in a matter of days? Today's vital agricultural boom could literally be brewing tomorrow's unprecedented public health crisis right beneath our feet. So the next time you pour yourself a glass of tap water and hold it up to the light, remember, the most dangerous things in our world are often the ones you cannot see.